Volition is the capacity of an animal to act driven by its own reasons as an agent to fill its own needs and to make decisions independently of external inputs. In us humans, this capacity is highly advanced, involving very complex processing that allows us to imagine and plan in our own internal virtual realities or imaginations before ever executing any real actions in the world. Clearly, having a well-thought-out plan in place before acting results in better thought-out actions. But most things in life and in evolution have simple beginnings, and it's unlikely that our very distant ancestors could weigh options in light of elaborate world models and a complex imagination such as ours. Nonetheless, they might have been able to initiate actions in the absence of any external impetus, on the basis of internal drives or other endogenous reasons that were their own. What might have been the earliest humble beginnings of free will? Why would a capacity for endogenous decision-making and self-initiated action have evolved in the first place, even long before the evolution of consciousness or conscious imagination? Even in very simple organisms, say as simple as a leech or even a paramecium, it's important not to be predictable. Any animal that's highly predictable would make easy prey because a predator could just wait for it at the place that it is predictably going. So, even in the absence of a capacity to plan, any animal that moves will likely evolve mechanisms to act and react in ways that predators can't foresee. One ancient example is the case of certain bacteria that have a flagellum. If the flagellum is rotated one way, the bacterium moves forward. But if it is turned the other way, it tumbles, orienting it in a random new direction. Once animals became metazoans, which were initially interlocked colonies of microorganisms, they lost that kind of mobility and had to invent new ways of collectively moving around. These cell collectives had to also evolve ways to move unpredictably, particularly when hunted by a predator. Both predators and prey evolve ways of predicting each other's next moves in an arms race among their perceptual, planning, and motor systems to predict the other's future moves. One result of this arms race was that animals became unpredictable, driven by their own invisible plans and drives. Even in the absence of complex conscious evaluation of options, many animals, such as cockroaches, have evolved escape responses that involve a form of constrained randomness. When something disturbs them, they run at a few set angles away from that thing, but which one is selected appears to be random and is switched among these set of angles randomly. This makes it very hard for a predator to predict where a cockroach will be in the next moment, making them hard to catch. How might such randomness of behavior be realized in the insect brain? Those who study turning behavior in flies suggest that their brains operate in a domain called criticality. In this domain of near chaos, a tiny difference in initial conditions can be amplified to radically different outcomes, like deciding to turn this way versus that. This is one example of a nonlinear process where outcomes in neural processing can come to differ radically despite apparently identical inputs. One question we'll return to later is what possible sources of neural noise might be, and how random fluctuations might be amplified from a microscopic domain of quantum domain chance to the macroscopic domain of neural spike timing variability, and ultimately to variability in behavior. Internally generated variability is not only important for being unpredictable, it's also important so that animals can learn. Animals try this, and then they try that. And the feedback that they get from the environment or from their social peers serves to reward or punish certain of these behaviors. Well-understood mechanisms reinforce those behaviors that are rewarding and downregulate those that are not rewarding or even punishing. But is the variability in animal behavior subject to internal control? In animals as diverse as Drosophila and humans, animals tend to increase the variability of their behavior when faced with novel situations, which might be thought of as exploratoriness. In other situations where there's a little novelty or the solution to a problem is familiar, responses tend to be more stereotyped, and in humans we might call these habits. Because all animals face a spectrum of problems, from the very novel to the stereotypical, most animals are able to behave in a range of ways, from exploratory and flexible to stereotyped and inflexible. Lovely work with fruit flies suggests that they can control the degree of variability injected into their own neural processing depending on the kind of problem that they're facing. And this capacity to up and downregulate variability in neural processing is not driven by the stimulus, but rather processing that's internal to the fly. Thus, under identical input conditions, a fly might act or not act, or might act with high or low variability. In other words, even in much simpler nervous systems than our own, under identical starting conditions, there are times when animals decide on the basis of purely endogenous factors to do this or that. And they could have done otherwise since their responses were probabilistic, perhaps resulting from amplification of randomness in the microscopic domain to randomness in macroscopic neural and behavioral domains. Another important reason that animals have evolved endogenous, that is, internally generated, versus exogenous, that is, driven by the stimulus, modes of acting and deciding, is that animals have to know whether changes in the world or stimulus are driven by self-actions or events in the world. At the very least, animals have to discount self-generated changes in the input as spurious, or they might take self-generated changes in sensory input to be due to changes in the world. Even in relatively simple animals, neural circuits, such as the corollary discharge circuit discussed in a recent section, allow an animal to distinguish self-generated from non-self-generated consequences of its own actions. This affords the beginning of a model of the world as that which happens independently of self-generated actions and processing, and it affords the beginning of a model of oneself as that which causes and results from self-generated actions and processing. An animal, even an animal as simple as a fly, can learn the consequences of its own actions. It can learn that it can control certain consequences of its actions, for example, that turning left will make the visual array appear to move in the opposite direction, and it can learn that it cannot control other things, like that which happens in the world, independently of its own decisions. Another reason that endogenous modes of processing evolved was to allow an animal to process identical inputs in flexible and varying ways depending on the needs of the animal. A key instance of this is endogenous attention. This allowed animals to focus on what was relevant and to ignore what was irrelevant. Given control of the sensors, such as where the eyes would look next, the brain could take control of its own future inputs for its own internal reasons. For example, if I'm looking for my keys, I'll look at likely places where I might have left them. But if I'm looking for my kids, I'll search an identical scene in very different places. In more advanced animals that have evolved a working memory, the model of the world and the model of the self can operate entirely in the absence of external input over internal representations. How might have this gotten off the ground? Imagine a fish that lacks working memory. It's driven by its inputs. If it sees a barracuda, it flees. But if the barracuda swims behind coral, it can no longer respond to it because it can't represent it because it's no longer in the stimulus. Now imagine a new revolutionary kind of fish that has a working memory. It can represent the barracuda even though it is no longer visible. It can play out internally that the barracuda is going that way, so it will flee that way. The evolution of a working memory afforded the ability to play out events before they happened inside of an internal world model that includes a model of the self in that world model. This revolution in nervous system design afforded an escape from so-called garden paths. A garden path occurs when locally, on the basis of present input, this is the best option, and then this next thing is the best option, and so on. But at the end of all these locally optimal choices lies something bad, like the jaws of a predator. In contrast, once working memory evolved, there was the possibility of desert paths where locally I have to do without, and locally I have to suffer, but at the end of the process I get something desirable, such as a mate, or shelter, or food. This advantage is highly elaborated in advanced animals such as ourselves and allows us to pursue aims not on the basis of sensory input, but on the basis of invisible goals and complex cognitive maps of the world and ourselves. In addition, teleological drives, such as thirst, lust, and hunger, drive animals to seek out that which might not be visible in the present set of sensory inputs. Operating within an endogenous model of the world, within an internal virtual reality, afforded tremendous freedom to play events out before doing anything in the real world. This ability to play things out internally required the evolution of endogenous operations that in us are highly elaborated in our tremendous powers of imagination. Such operations are not driven by the input, they're driven endogenously. Such endogenous processes are the root of volition and freedom. Freedom from being stimulus-driven and freedom to explore and act within an internal world model. This is not an all or none state of affairs. In us humans, endogenous volitional processes are highly elaborated, but even in much simpler animals, whether fish or flies, there are endogenous operations over internal representations that are subject to control for internal reasons. Thus, free will comes in degrees. Its beginnings were humble, and in us reached a degree of elaboration that gives us, in comparison to other animals, something approaching the freedom of gods.